In today's video, we're going to take a little bit more in-depth look at temperature and how it relates with intermolecular forces to affect the boiling point of different substances. So I'm starting off with this definition. It should be in your notebook already, but make sure it is. Temperature is the average speed of particles in something. Another way we could think about it is kinetic energy. So when we're talking about the speed of particles, that's a form of kinetic energy because they're moving around. Which leads me to this. So make sure to have this in your notebook as well. When something is a solid, those intermolecular forces, another way we could think of it as their attraction to each other, is going to be much, much greater or much stronger than that kinetic energy. So we could think about it if we have some water molecules here. Their partial negatives are attracted to the partial positives on each one. And they still have some kinetic energy, so they'll be moving, they'll be vibrating, but they're still going to be in the same position with each other. They're not moving past each other. They're still kind of locked in place, even though they're moving. So this is when our attraction is much greater than our kinetic energy. So if we heat that up a little bit and make it a liquid, our intermolecular force, our attraction, is still going to be a little bit greater than our kinetic energy most of the time in general. So they'll be still attracted with each other, but every once in a while, one might break off, attach to another one. So now they're moving back and forth, but they're still, breaking and forming these intermolecular forces. So in general, they're still getting attracted to each other more than they're just flying all over the place. But then if we heat it up more, that transition between liquid and gas, that's when our kinetic energy starts becoming much, much greater than our intermolecular force. So now they're not even going to be really that close to each other. In a gas, they're flying all over the place. It's like they bump into each other, they go apart. Their intermolecular force, their attraction, is not enough to keep them held together, and their kinetic energy is too strong to keep them together. So their speed is too fast to hold them together, and they just fly apart. So we're going to make a graph today. That's our main thing we're doing. And it's going to show energy on our y-axis, and we got temperature on our x-axis. And we're going to be taking a look to kind of compare the different intermolecular forces between substances by looking at their boiling point. So the first thing I'm going to do on my graph is I'm going to draw a line here, kind of diagonal. And I don't got units on my energy because we're not worried too much about units. We just want to know if something has more energy or less energy than something. So I'm just going to draw a line up here. And this is going to be my kinetic energy. How fast are my particles moving? And you might have a question, why do I have negative 273 degrees right here in my bottom corner? And that's what we call absolute zero. So this is the temperature where it can't get any colder than that. That's when our particles have stopped. So you can't get any less motion than no motion. So that's absolute zero, zero kinetic energy. And then as we warm up, as our temperature increases, our kinetic energy will increase. So now let's take a look at some different particles here. So we got neon. And neon has a boiling point of 246, or sorry, negative 246 degrees. So I'm going to put it right around here. Seems about right. So at this much temperature, that's when I'm going to write neon over here. At negative 246, that's when neon starts boiling. So that's when the kinetic energy starts becoming stronger than our intermolecular force. So this line here will represent the attraction that neon has with itself. So that's the intermolecular force that neon has. And neon is it's a small atom. It has 10 electrons. It only is attracted with dispersion forces, so it has a fairly low intermolecular force. So it has a very low boiling point as well. So if we take a look at another particle, this one will be a molecule here. This one will be an oxygen molecule. So if we take a look at it, it is non-polar, which means just like neon, its strongest intermolecular force is going to be dispersion forces. But it's a little bit larger. So it's got two atoms there. They're bonded together. So it's going to have a little bit of a stronger intermolecular force. So an oxygen molecules will boil at about negative 183 degrees. So the energy that these intermolecular forces have are about this much. So we're going to call this O2. So when it is colder than 183 degrees, the intermolecular forces are strong enough to kind of hold oxygen together in the liquid or solid state. Once it gets warmer than negative 183 degrees, the kinetic energy is stronger, and it becomes a gas. All right, let's take a look at some other ones. So we got formaldehyde, or CH2O. And formaldehyde has a boiling point of about negative 20. So this one will be significantly stronger. So about negative 20. And that's because you may notice this is a polar molecule. So oxygen, it had no partial charges. It's non-polar. Formaldehyde, it has partial negative by the oxygen and a partial positive on the other side of the molecule. So these have they have a stronger attraction with each other. They have what we call dipole forces attracting each other. So because they have that stronger type of intermolecular force, it's going to take a lot more kinetic energy to pull them apart. You could just look on a graph. You could see how much more energy it takes to pull those apart. So it'll be right about here. And that'll be formaldehyde. I guess I'll write that on the side. Some of you may have heard that term before. All right, and that one is attracted from dipole forces. So let's take a look at another molecule. This one will be ethanol, and it has a significantly higher boiling point. It has a boiling point of around 78 to 79 degrees Celsius. We'll say 79, we'll round it up. And if you take a look, this is also going to be a polar molecule. So it has this oxygen here, which will have that partial negative. And it has hydrogen here that has a partial positive, and over here there'll be a partial positive as well. So it is polar. But something that might make this molecule have a stronger intermolecular force would be this bond here between the O and the H. That's going to allow it to form hydrogen bonding with other molecules like this, which is a much stronger intermolecular force. So it'll take even more kinetic energy to pull them apart and turn it into a gas. So this one will be ethanol. And it's going to have some hydrogen bonding. And the last molecule we're going to be looking at today is one that we commonly look at. It's going to be water. Water has a boiling point of 100 degrees Celsius, so it even has stronger attraction than the ethanol we talked about. And if you take a look at it, it also has hydrogen bonding. So you might think, why does it have a higher boiling point if it uses the same intermolecular force? And that's because, let me draw the partial charges here. That's because it can form multiple hydrogen bonds between itself. So here will be partial positive, partial positive. You could see it could form hydrogen bonding between this H and an O, and it can form hydrogen bonding between this H and another O as well. So if I had multiple water molecules together, you could see we got multiple hydrogen bonds going on within the same molecule. So it's very, very attracted to itself, which means it takes even more kinetic energy to make it become a gas, to kind of break up those molecules. And we could see similar things. I'll put this up here. These are all boiling points. So it'll be the temperature down here that it goes from a liquid to a gas. So we could see that the stronger the intermolecular force, the higher the boiling point is going to be. And we can see similar things with melting point as well. There's a few more things that go in with melting point, like their size and their shape and how they want to form a solid structure together. But we should find an overall very similar pattern with melting point as well. I just wanted to show one thing with boiling point here. So our overall takeaway here should be that the stronger our intermolecular force, the higher our boiling point is going to be.